Okay, in this lecture, I'm going to talk about a very important concept that is pretty fundamental and something that we in physics sometimes take for granted, but it's really a profound thing to say, and that is that momentum is a conserved quantity. And in physics, we don't take language for granted. We say that conserved means that it can never be created or destroyed. So momentum that you start with in a closed system is the momentum that you end with in that closed system. So if we take the universe as our closed system, which we're totally allowed to do, this truth must be the fact, and the momentum that was created at the Big Bang is the momentum that we have today in our system. It's a pretty profound thing. And so, if you believe that the universe is a closed system. So for us, a system takes on a special meaning, and the surroundings also take on a special meaning. And as long as the system and the surroundings are things that we can quantify using the momentum principle and momentum, we can calculate the conservation of momentum within our system. And it's a fairly basic thing to say. Momentum can only be transferred between objects or within a system or between a system and a surrounding through the application of forces. And so we've talked about a few fundamental forces. We've talked about gravity, we've talked about electrostatics, and I hope that you've read a little bit about the nuclear weak and the strong force. And so a mathematical statement of the conservation of momentum says that the change in momentum for a system plus the change in the momentum for surroundings must be zero. And so that's where we're going to go now with this lecture. So let me expand on this just a little bit. So the system momentum that I talk about, that I've sketched out here, can be any number of particles that interact through any types of forces that we can calculate. And so these may be acting through some sort of gravitational force or some electrostatic forces, and they have some set of momenta that I am going to try and recreate over here. So this is P1, this is P2, this is P3, this is P4, and the net momentum for my system, this is P total. So that's the net momentum. I have superposed all of my momenta. I've added them up vectorially, and I get the total momentum of the system. Now that momentum can change, and within the system, the momentum can be any number of things. So for my system of particles, if this is the way I draw my system momentum, I can state that the momentum of the system is here, P total. Okay, so we'll use this, we'll come back to this as a way to start to calculate things like changes in momentum for more complex systems. Now, what I'd like to say is that we can make choices about what kind of systems we have. And so, for example, we could have two particles or two celestial objects interacting through gravitational forces. And let's say these are stars. So this could be perhaps star 1, and this is star 2. And star 1 and star 2 act on each other, and we can make a choice. We can say that one is the system and the other is the surroundings. They have reciprocal forces, right? The forces between them. This is the force on star 1 from star 2, and this is the force on star 2 due to star 1. And we can state that F of 1, 2 is actually equal to minus, or I should say, F of 2, 1 is equal to minus F of 1, 2. they're equal and opposite. And so I can think about, for example, identifying star 1 as being my system, which naturally makes star 2 as the only other thing in my worldview here as the surroundings. So this is going to be the surroundings. Okay? And so now we can go and calculate the momentum principle for everything. And when we do that, what we find is that the change in momentum, let's say one of these stars is orbiting the other, but the change in momentum of star 1 is equal to, well, it's the force net, which is the force on, it's the gravitational force on 1 by 2 in some time delta t. Let's say that this star is going on a trip around the other star, and that this star feels a force as this star goes by. And we can also calculate the change in momentum for our surroundings. And so the change in momentum, so this is for the system. And so we can say that delta P2, star 2, is equal to, well, that's F of 2 comma 1 delta T. That's for the surroundings. And with that, we can then write that delta P2 is equal to minus F1, 2 delta T. And so now, if we use our conservation of momentum principle here, delta P of the system plus delta P of the surroundings equals 0, we can try and prove that. So let's do it. Let's take the value delta P of the system, I'll make this surroundings, and now we have that F1, 2 delta T minus F1, 2 delta T, and by that we get 0, which is what we would expect. And so that makes sense. Okay. Now, what if we took a slightly different approach? Let's prove the same idea, but for a choice of our system being both stars. Still on this trajectory, but now I'm going to draw my circle a bit differently. I'm going to draw my system to include both stars. There's nothing else. There's nothing else around. And so the delta P of the system well, what's delta P of the system? It's going to be the force on this in some delta T. So F of 1, 2 delta T plus, well, it's the momentum change on this star. So let me just, delta P of the system is going to be delta P on 1 plus delta P on 2. And so this is going to be F of 2, 1 delta T. So delta P of the system, without any surroundings to worry about, gives us a very similar answer. 1, 2 delta T minus F1, 2 delta T. And so the change in momentum of the system is equal to 0. And so that's a nice clean way of showing that it doesn't matter if you choose a system and its surroundings or just choose everything within the system, you still get that the change in momentum of the system, the conservation of momentum, is still equal to 0. So delta P, meaning the amount of momentum that has changed within this system is identically zero because of the reciprocity of forces. And so that's why it's so important to understand these force pairs as being the equals and opposites of each other. It makes it so we can conserve momentum, which is a physically proven fact. Okay. Another way to think about the first example is that you can have momentum that can flow between your system and your surroundings. And so as one star exerts a force, it transfers through some mechanism of forces, it transfers its momentum to the other star in the surroundings. So you can have flow of momentum between system and surroundings. So everything has to balance in that case. Okay. So I'm going to write here, if a system is isolated. So isolation in the physical sense means that all the other forces and all the other interactions are negligible. We just ignore them, or they're so small that they don't really matter. So if a system is isolated, then the total momentum does not change for all time. So, in any system that is isolated, where there are perhaps two, perhaps a million, perhaps a billion things interacting, but they're only interacting with that set of a billion things, no outside, we can say that one is the system and the rest are the surroundings, or we can just draw a circle around all of them and say that that is an isolated system. Either way. But the total momentum does not change for all time. And what's great about conservation is it allows us to generalize our arguments for systems that aren't so simple. It allows us to just draw a box around our system and say the net momentum of that object, that set of objects, stays fixed.